Questions about lab? No questions? Okay. We'll pick up where we left off here. What are we doing here? Nitrating. And I say we'll do mononitration. Which ring is more activated towards the EAS reaction? The one with the methoxy group or the methyl? The one with the methoxy. It's a group 1. It can donate by resonance. It has a lone pair. This ring is more activated. Which position of the ring? Basically symmetrical. The position ortho to the methoxy or meta? Ortho. When you nitrate this, you're going to get that product. Nitration there. That's the main product. Questions about that one? Gifty?
Will you be wrong if you put it on the other side?
I'm sorry, I can't hear you.
If I put it on the other side, would that be wrong?
Would that be a different compound?
Yeah.
It would be the same compound.
Okay.
You named it, it would be the same exact name. No, it would be the same thing. Okay, any questions about substituent effects, activating or directing? We'll have a quiz on Monday. Okay. Through what we cover on Friday. We can confirm on Friday. Sulfonamide lab due on Friday here in class. There's 2 handouts today. One white one, one gold one. At this point, we're moving back to new EAS reactions and the Friedel crafts. We showed this mechanism last time. Carbocation here is your electrophile. This reaction works with primary, secondary, tertiary halides as long as they're sp3. Halide has to be on sp3. It does not work if the halide is on sp2. So it doesn't work with these guys. Chlorine is your most common, but it does work with bromine iodine. But typically chlorine is much more common. Because chlorine is your cheapest halogen, and it does work. With the primary halides, it's probably not a primary carbocation, but we're not going to look at what it might be. Okay, up here we made a secondary carbocation, right? Those are okay. Tertiary certainly is easiest. Let's look at other routes to carbocations. What other ways have we made carbocations either in organic 1 or 2? Well, last test we made carbocations from alcohols. You make a carbocation from alcohol by protonating it, and then the water ionizing, and you can get carbocation. That's best with what type of alcohols? Tertiary. Like we got cut off. Best with tertiary alcohol. Also with alcohols you can use a Lewis acid. And BF3 is a common Lewis acid with alcohols. Where's boron on the periodic table? Pardon? Let me check my periodic table. Right to the left of carbon. Okay? Right above aluminum. Makes 3 bonds. It's just like aluminum. Okay? Aluminum and boron are both common Lewis acids. These electrons can add to the boron. We can get BF3 minus, and that is a plus. So instead of protonating it or making a positive would be by protonating it with H+. We protonate it, essentially we give a positive by complexing with the Lewis acid. At this point, the OH can ionize, or the oxygen can ionize off, and that will give you carbocation plus BF3O minus. Now, minor point, BF3 is not actually a catalyst when you use it because it's not reproduced, it's not regenerated. Instead of losing the hydroxide, you go back to BF3, it actually loses an F minus. And so it's, whenever you use it, it's not actually a catalyst, but that's a very minor point. So, a new way to ionize an alcohol, analogous to protonating it. Simply using a Lewis acid. What other ways have we seen to make alkenes? As soon as you make your carbocation, well, then the ring can attack just like it did up there. We also make carbocations from alkenes. Yeah? In Organic 1, that's the first way we made carbocations. At least my guys. So an alkene can attack an H+. If this attacks H+, you're going to leave carbocation on the left or right? On the left. So it attacks, it pulls away from the left, and it gives this carbocation with new H added there. But this carbocation is the same one we made in the mechanism above from an alkyl chloride. In the end, there's different ways to make carbocations. I can also make this carbocation from what? Maybe taking this alcohol here. What do I need to do to make this carbocation? Need to get that to leave? How do you want to get that to leave? Protonate with H+. What new way do we know? We can also treat it with BF3, complex and then ionize. So, multiple ways to make carbocations. The ring doesn't care how you make the carbocation. As soon as you make it, it'll attack it. With H+, down here, what are your most common catalysts? Because it will be a catalyst down there. Sulfuric, phosphoric, HF. You typically don't want to use like HBr because instead of the ring attacking the carbocation, Br minus could attack the carbocation. If that happens, well, you're doing different chemistry. You don't want a competing nucleophile. That's the same old story. I think I've said that about 5 or 10 times, about every other month. You want an acid catalyst, you use certain acids, those that do not have a competing nucleophile. Okay, so that's the Friedel-Crafts alkylation. Friedel-Crafts, by the way, were back in the 1870s or 80s. One was a professor, one was a student. I can't remember which was which. And they really showed this chemistry, how it worked. Okay, the Friedel-Crafts has limitations. First limitation is it fails with strongly deactivating subs. And because of such limitations, for us to understand that, that's why we had to first do the activation-deactivation. Okay? Friedel-Crafts doesn't work with strongly deactivating subs. Which ones are your strongly deactivating subs? Group 4. Group 4 is also known as what type of directors? Yeah, Group 4 are your meta-directors. Friedel-Crafts doesn't work when you have a meta-director or a strong deactivator. For example, if you try to do a Friedel-Crafts alkylation just like we did our mechanism with nitrobenzene, it won't work. Because nitro is a strong deactivator. Why will it not work? Well, apparently it just don't. Okay? I mean, you can react nitrobenzene with bromine and FeBr3, and it will give what? What are we doing here? Brominating the ring? Where's it going to go? Yeah, this will work. But it won't do the Friedel-Crafts. So there's a fine reason why, okay? Apparently it's just not a reactive enough system. And in general, 99% of the time, if you have a metal director, strong deactivator, it won't react. In fact, nitrobenzene is often used as a solvent for Friedel-Crafts reactions because it doesn't react. Another limitation. Friedel-Crafts reactions don't work with anilines. Somebody tell me why. Is this a strongly deactivating sub? No, not as it is. But what's the first step of this mechanism? Alicia?
Coordinate attacks the ALC.
So these long pairs coordinate with the aluminum. Do your acid-base chemistry, Lewis acid-base chemistry. What's to keep this long pair from doing that? Absolutely nothing. The amine is basic enough that it will react with the aluminum. And once it does, what do you get? I'm just going to call that phenyl. You got two H's there. And this is a bond to the aluminum, Cl3. That's now a minus. This is a plus. What did we turn our amine into? It's no longer a strongly activating sub. What type of group is it now? It's an electron-poor atom with no lone pair. What type of group is it now? It's now group 4. Complexation with the amine, with the aluminum trichloride, turns it into group 4 here. And now what do? You refer to problem number 1. The reaction doesn't work when you have a strongly deactivating sub. Okay? Refer to that. But we kind of pointed this out before. Go back to the activating, deactivating. This big line over here. What happens to amines with an H plus or Lewis acid? They become protonated or they become a positive charge, and now they become strongly deactivating. So this is an example of that. You can't say, okay, I mean, when I add the aluminum chloride, I don't want you to react. I just want the Cl to react. It won't listen to you. Another problem with the Friedel-Crafts. It's only a problem if you don't want it to happen. But that's rearrangements. What are carbocations prone to do? Rearrange. If you try to, now we may have to kind of look the other way a little bit and make a primary carbocation. You try to react benzene with butyl chloride, Lewis acid, to try to put this group on. If you do that reaction, you only get 35% of that. You also get, instead as the major product, 65% of this. How do you get the major product? First step is this coordinating with the aluminum. And we get 1, 2, 3, 4, 1, 2, 3, 4, chlorine, AlCl3 minus, plus, I'm going to have to show a primary carbocation here. This ionizes off. We get the primary carbocation plus AlCl4 minus. How do you get product A? Benzene ring attacks there. Yeah, same old mechanism. You may not even want to write it down. I'm pulling away from the bottom carbon, so I'm going to make a bond there. There's an H. Carbocation here. Resin stabilized. From there, we take the H, restore the aromaticity, and we get the product A. How do we get the lower product? Apparently there was a carbocation on the second carbon. What do we do? Hydride shift. We have two H's here. One of them can move over, and we get secondary. And somebody should say, hey, wait a minute. That's a resonance error. These aren't resonance structures. Those are not resonance structures, right? And then the ring attacks here. I can understand that. I'm not going to go through all this. This has all been done several times. I mean, refer back to the mechanism, right? We don't want to waste 30 seconds writing this down real quick. You already have it written down. Okay, this is your mechanism from here. The main point is you either attack the primary to get the A, but the major product is where you attack secondary. Okay? Apparently the primary cation exists long enough to attack and give some, but majority rearranges and you attack the secondary. Again, there's some argument here whether it's really a true primary carbocation. I'm not going to get into that. For us, typically we want to avoid primary carbocation. In a little bit, we'll show a much better way to make A. We'll show a selective way to make A in high yield. A two-step approach. The one-step approach gives the other compound as the major product. Always be aware of rearrangements for carbocations, right? Another problem with the Friedel crafts is polyalkylation. Take benzene, react with isopropyl chloride, Lewis acid, you can make isopropyl benzene. But the reaction has a tendency to not stop there, even if you want it to. It'll put a second group on. Question, which is more reactive towards an EAS, benzene or isopropyl benzene? Which is more reactive? Isopropyl is what type of group? Group 2? It's an alkyl inductive donator. Okay? So this is more reactive than the starting material. So let's say this reaction has gone 10%. 10% has reacted. 10% of this is formed. Okay? And 90% of this left to react. Well, as soon as this is formed, it's more reactive. And so, instead of this attacking and completing the reaction, doing it 90% more times, this starts reacting. And this is more reactive, so it's going to react faster and easier. I mean, what if it were at 50%? That means you've got 50% of product made, 50% of this. Now you've got 1 to 1. This is going to win out. And it'll react and give this. By the way, is this an orthopara director or another director? Orthopara. I showed para. We can also say it's going to also give ortho, but okay. Now which is more reactive? One isopropyl or 2? Now this is more reactive than that. As soon as you start forming some of this, it's going to start reacting. Here I come, get out of the way. Okay? Now you've got 3 groups on. Now which is more reactive? As you put another group on, it gets more and more reactive. And you end up with, if you try to use one equivalent, and say, I'm just going to use one equivalent of this because I only want one group, it don't matter. You're going to end up with maybe 30% of that, 30% this, 30% this, and 100% of nothing. Typically, you have to just drive it all the way to get a good yield. You have to maybe just say, well, I'm going to use 3 equivalents and drive it all the way to this, and then maybe at some point it'll stop reacting because it gets too sterically crowded. This is a real problem in practice. One way to overcome this is to use a huge amount of the starting material. Huge amount of this. That way, even though there's a million molecules of this form, there's still 100 gazillion of these, and it just wins out because there's just more of them. You can only do that when you can get rid of this and it's real cheap. For example, just using benzene. This is a true problem, and thus, this is a real major problem. Because of this, Friedel-Crafts alkylations are difficult. It can be made to work out in practice. It takes a lot of research to get the conditions just right. We will say that this is not a good reaction typically, and we're going to prefer a 2-step route. The 2-step route will solve problems 3 and 4. Nothing's going to solve problems 1 and 2. Okay, now let's look at Friedel-Crafts acylation. I'm going to give ketone. Acyl is sort of a slang name for a kind of a ketone group. You know, somebody could have called it a ketyl, but instead it's acyl. Mainly because a methyl ketone is an acyl group, and it just any ketone is also called an acyl. And so we'll do this by the Friedel-Crafts acylation. Very similar, except instead of using an alkyl halide, we use an acyl halide. And again, the most common are your chlorides. So acyl chloride, carbonyl chloride. Sometimes called an acid chloride because it comes from carboxylic acid. Now the R group can be anything because the R group here, your chlorine is not on the R group. So it can be anything. It cannot be H. It cannot do this because that's not stable. Point that out because later on you guys typically try to use that for a certain reason, but that's not stable. There's a tricky way to get around that. I'll show you later. Okay, the mechanism is very similar. First step is your halide complexes with the Lewis acid, and we get the complex. We're making a benzene ring carbon to carbonyl bond. At this point, the chlorine will ionize, and we get this carbocation plus AlCl4 minus. This carbocation may look a little odd. What's the name of this? We've seen it before. What's the name of it? Where have we seen it? got an organic 1. Where do we see this? Mass spec of ketones. What's the name of this carbocation? Comes from an acyl chloride. We're putting the acyl group on the benzene ring. What's the name of this cation? Acylium ion. Remember seeing acylium ions in mass spec? How does this cleave in mass spec? It cleaves here to give what? Acylium ion plus radical? Acylium ion for mass spec. Look back at your mass spec. Why does this cleave here? Why does it do alpha cleavage? Why is it more stable? Because it's resonance stabilized. Now, what's the hybridization of the carbocation here? I see a single bond and double bond. I see 2 regions around it. What's the hybridization? 2 regions is SP, right? SP. It's actually linear. You see, that should be linear there. I'm going to draw it linear here. There's your carbon. That should be linear. This moves in, you have triple bond now, positive charge on oxygen. And that's your major resonance structure, because it has more bonds. This is a resonance stabilized acylium ion. Okay, it may look a little odd because it's on what was originally an sp2 carbon. And on the previous page we said we don't make carbocations on sp2 carbon. Right here. These cations not stable enough to form. Yeah, they'd be from sp2 carbons, but they would not be resonance stabilized. This one is resonance stabilized. It will form. Because it's resonance stabilized, it does not rearrange. Because it does not rearrange, that solves one of the problems of the alkylation. When you do acylation, you don't have to worry about rearrangements. Because your acylium, it don't rearrange. Now once you get your carbocation, then the benzene ring attacks. What does that give? It gives you sigma complex with an H there. I'll draw in the carbon. We just made that bond. Plus charge there. Here's your resonance stabilized sigma complex intermediate. From there, what do we need to do to get final product? Chlorine says see you later. Takes the H, these move in. You get that plus HCl plus what? Plus your AlCl3 reform. And so your good old standard EAS mechanism. What's the electrophile here though? Acylium ion. Acylium ion. Made by complexing acyl halide, usually chloride with aluminum trichloride. You don't have to worry about rearrangements, so problem number 3 is not applicable here. What about problem 4? Polyalkylation, polyacylation. Which is more reactive, starting material or product here? Stanley, which more reactive? Benzene or... If the R group was a methyl, what would be the name of that compound? acetophenone. Which is more reactive towards EAS, benzene or acetophenone? Humma? Humana? Anything special going on today, Humma? Nothing going on today? Acetophenone is what? Yeah, that's it. What about it?
Is it more reactive?
It's more reactive? Would that electron core carbon bond into it? What type of group is a ketone? Group 4, electron core. No, acetophenone is less reactive than benzene. In fact, will acetophenone even do a Friedel-Crafts type reaction? What was rule number 1 on the previous page? If you have a group 4 deactivator on the ring, you can't do a Friedel-Crafts. Still applies here. That can't even do a Friedel-Crafts. So is it going to polyacylate? No. You don't have any problem. Problems 3 and 4 are not applicable to acylation. Acylation is much better reaction thus. You still have problems with 1 and 2, but 3 and 4 are no longer applicable. So, there's no polyacylation. This won't even do a Friedel-Crafts reaction. So you get a good yield of that. Now, remember compound A on the previous page. We can show a two-step route to compound A. We'll also introduce a new reaction. Compound A was shown on the previous page. We got low yield because it rearranged instead. We can make compound A in a higher yield by a two-step process of putting an acyl group on first. We want 4 carbons, so we want a 4-carbon acyl group, with the first carbon being a carbonyl and then 3 saturated carbons. We can put that on in high yield. Then there's chemistry where we can remove the oxygen from the first carbon, which is known as what? What's that first carbon known as? Benzylic carbon. We can remove the oxygen. That would be a reduction, wouldn't it? Remove oxygen. We can remove that oxygen 3 different ways. Hydrogen plated on carbon. Hydrogenation. Hydrogen, your favorite precious metal catalyst. Nickel, rhodium, whatever you like to use. That will do it. We will not look at a mechanism. The traditional old textbook way is the Clemmensen reduction. Very classical textbook. Using a dissolving metal reduction, using zinc. You have to include a little mercury with it, so it's an amalgam. HCl. It's called a Clemmensen reduction. That will remove the oxygen and give you just a CH2 there. Effectively replacing the oxygen with CH2. We're not going to look at mechanisms for these first 2 reactions. It is a reduction. Note that the first 2 steps were also used to remove oxygen from nitrogen. Remember, in fact, we're doing something like this today. So zinc HCl will also reduce your nitro group. Here it removes the oxygen. It does not cleave a carbon-carbon bond. The third way is the Wolff-Kishner reduction. We will not look at this mechanism now, but we will look at it during test 4, when we look at carbonyl chemistry. This uses hydrazine and hydroxide. It's a very classical mechanism. It's very unique, interesting. When you see it, it'll look straightforward and you'll say, wow, that's interesting. So for now, 3 different ways to do it. We're not looking at mechanism of any of them. What does it do? It removes the oxygen. 4-carbon acyl becomes 4-carbon here. In this way, you can get a high yield of A, where if you try to put the group on directly, the yield would be low because of rearrangements. What is the 2-step process? What's the first step? Acylation. Real press. Acylation followed by reduction. Much better than direct alkylation. Here's that comment again. This is not stable. Sometimes you guys, when we do multi-step synthesis, try to put on this group using like this acid chloride. Thinking you're going to put on that group. It's not stable. There's a trick though. You can use, instead of this, you can use CO and HCl. Carbon monoxide HCl. And your Lewis acid, because this will generate that in equilibrium. I wouldn't even show you this, but because I usually always get a 2 or 3 to try to do this, I have to kind of say, hey, that's not stable. But let me tell you about this. It's an interesting reaction. I think it's known as the Goderman-Hock reaction. I can't remember. By the way, I showed that right there over here. It produces that in situ in the reaction or in the mixture. Okay. Let's predict some products. Show the product of the first reaction. Somebody got it?
No reaction.
No reaction? Why no reaction? No, there is a reaction here. You said the chlorine can bond to the AlCl3?
Oh, the chlorine. Yeah. Could it also, the way the low carbon chlorine possibly bond with AlCl3?
It possibly could. Sean?
Your carbon attached to the other ring, over the fly.
You get ortho to the fluorine and para to the fluorine. type of director is the F? What type of director is the F?
Group 3.
Brittany? What? It is group 3. What type of director is it? Ortho-pair. You get ortho and pair. Ortho-pair directors give both predominantly. You get mixtures. You have to separate them unless you figure out how you can get one over the other. Typically, pair may be more favored because it's less sterically hindered. It's not right next to the group. Ortho-pair directors give two major products. We have to deal with having mixtures. Questions about this one? Alma, what were you looking at? What was the issue?
Well, I just saw the flooring, and I just automatically assumed that the lone pairs on the flooring to directly attack the ALCL3 causing a no reaction, but I didn't think of like the other way.
Okay. Well, let's go back and look at what we showed. We showed, I think you're referring to fails with anilines?
Yeah, I think that's what
Yeah. And I didn't say it fails with aryl halides. I didn't say it fails with, okay. It doesn't fail with phenols. It works with phenols. It works with halogens. Okay. Yes, these have lone pairs, but since it works, apparently these do not complex as tightly with the aluminum and ruin the reaction. Why does the nitrogen apparently complex greater? Because nitrogen is more basic. These others will react. Other questions about this one, Mark?
Is that the O with the Cl before and strong deactivator?
Strong deactivator?
Yeah.
Yeah, this ring is not going to do a Frito press. That's the ring that's doing the mechanism. What? This is the acetylene ion. Okay? But that's important. I suspect there's just because I put the acid chloride on the left and not on the line doesn't mean anything. You have to identify what's the acid chloride, what's the reacting ring. I gave you two rings. Why? Because I want you to determine which ring is reacting. This becomes your acetylene ion, and this ring attacks ortho-para. You know, that ortho, and then you can do it para. Just because there's a benzene ring here doesn't mean it's doing any chemistry. Yeah, you're right. That benzene ring has a strong deactivating group. It can't do Frito prep. Okay? Both of these are in the flask. It don't matter where I draw them on the board. So, a couple of good questions. Any other questions about this? You've got to be able to assess things out of immediate context. Okay, next one. I gave you a hint. Think intramolecular. There's only one molecule here. Okay, let's take it stepwise. What is aluminum trichloride going to do? React here, ionize. Does everybody agree that we can get an acetylene there? By complexing ionize, you can show that mechanism. Okay, what could attack the acetylene? I only see one benzene on the board here. This? Okay. What type of director is on this ring? An alkyl. What type of director is that? Ortho pair. So which carbon is going to attack this? The ortho or the pair? I think the ortho, because the pair is going to have a hard time reaching over there. This is set up to do an ortho internal. Okay? These electrons can attack. We get bond to the carbonyl with 1, 2, 3. We got two CH2, CH2. Okay. There's an H here. What is on this carbon at this point? Carbocation. All right. And now your AlCl3 with an extra chlorine. See you later. Take the H, restore the aromaticity, and what do you get? You get that 6 and 5 fused together, where we made this bond plus ACO plus aluminum trichloride. Matt?
Why can't this one also go para?
I mean, you're going to have a tough time making this big old bond from over there to that site over there. It's just, that'd be an ugly looking, very long bond. You can get some type of stuff like that, depending on the flexibility of this ring. It's not that flexible here. There are some examples. This is going to be ortho kind of preferred. Okay, there's two below. I want you to do those on your own. These are just, in all these reactions, we're making some type of carbocation, either acylium or more of a saturated carbocation. Can you envision a carbocation up here? Yeah. Can you envision a carbocation here? Alkenes? Okay, we showed. Okay. Make your carbocation and then react. Look at those. Let's take a look at a couple of miscellaneous examples here while we're on this page. There's a synthesis of Tazorac used as an acne medication. Multi-step synthesis. Look at the first step of this synthesis. Well, it's not the exact first step. Going from 16 to 17. What are they doing there? They're somehow making a bond from this carbon to that carbon. They're making this bond. How are they doing that? I said, there's an EAS. There's an H here. Now the H is gone and we have a new group. Don't worry about P2O5. H3PO4, H plus. They're making a bond to carbon. When you make bond to carbon, it's typically a carbocation. Either a plain carbocation or an acylium. This is a Friel-Crafts reaction. How can we get a carbocation over here? H plus. If this alkene reacts with H plus, so we're going to make carbocation on left or right?
Right.
Correct, right. So this pulls away, and we get that carbocation with new H there, and that is boom, boom, sulfur. And that's just an organic 1 reaction, right? Protonation of the alkene in the appropriate position. Now you got this carbocation right next door. What type of director is this sulfur? It's an atom with a lone pair and it ain't halogen. Group 1, activator, what type of director is it? Ortho-para. This ortho position is activated. These electrons can just boom. Right there next door. Right? Eventually you get that there. You can look at it. You got to remove the H plus to reform your phosphoric acid. That's just an example of this coming from an alkene. How do they get that? They first do a Williamson ether synthesis. Sodium hydroxide makes the anion, and then the anion, boom, does an SN2. That's how they get that on. They also do another Friedel-Crafts. Actually, after 17, they didn't turn around and do another Friedel-Crafts. What do they do going from 17 to 18? They're putting this acyl group on. How do you put acyl groups on? Friedel-Crafts acylation. Where is it going? Which is going to direct, the sulfur or the carbon group? Sulfur is a stronger activator. It's going to direct. And it's ortho-para. Ortho is here, here, or there. That's blocked. If you go ortho or para, acid chloride, they're not using aluminum trichloride. Instead, they're using tin 4-chloride. Tin 4-chloride is another Lewis acid. It's not as strong as aluminum. It's your Lewis acid. First step here is this complexes with the tin, then it ionizes, and then the attacks acylium. They don't say what the yield is. They may have also gotten some where the acyl group went ortho. I don't know. They don't say what yield. Maybe they only got this in 40% yield, and they had to just remove the other. So there's two Friedel-Crafts. You can look at some of the other chemistry. The very last reaction is a palladium reaction. For Friday, please have completed a multi-step synthesis of this compound, starting with benzene. Try the others. The second one you should be able to do also. The first and second you should be able to do. The very last one you should be able to do. I'm not sure you can do the third or fourth yet. Please be working on those. We'll look at those first thing next time. Everybody got a handout today, one gold, one white. Please return those if you will. The extras. Okay guys, see you soon.
I'm late every day. Yeah, man. What's up with that? What? Alright, so how do you do the print? Yeah.